Howdy hackers, and welcome to another episode of FairLight TV. Today we are going to have a deep and detailed look at a very intriguing aspect of C64 coding. Stable rasters. Yeah, it's 99% of the use cases where this is relevant is for demo coding. And I'm not a demo coder, so this will be my best understanding of stable rasters. And if you're not a C64 demo coder, you might still find this interesting because it is a rather intriguing topic. So let's go over to stable rasters. Okay, Pontus showing his PowerPoint. That's sort of a new thing here, isn't it? So just to give you kind of the brief background, the screen on the C64 is drawn like line per line. So think of it like somebody painting the line, painting the next line, painting the third line and the fourth line, and so on. And then you have a wrap here at the end of a line, and when a new one starts, it's called what would that be, a horizontal blank, I think it's called, when that one is jumped. And then you have the vertical blank when all of the screen is drawn and the last line is drawn. It's wrapping around and starting on the very top again and starting to paint the lines. And you have the border there, and then you have the visible screen, and a number of the Victrix that are applied to any program on the C64 where you want to kind of utilize the more sophisticated Victrix. Most of the times you need to poke a value in the Vic at a very specific cycle. So I mean, if you think of it like drawing, it's you need when that raster beam is at a very specific point on the screen, you need to apply that change to the Vic register just there. If you are like one cycle off before or after, the effect does not happen. That's typically it, or at least it gives side effects or whatever. But if you think of like the really simple case, if you are drawing and you are making a change to the color register, and then you let it kind of slide a bit, and then you make another change to the color register, and then on the next line you do the same, then you get like a vertical bar just because of that. But you need to have that really consistently poking at the very specific cycle on the screen, because if you are sort of jiggling a number of cycles back and forth, that bar is not going to be like a bar. It will be something that is sort of flashy, which is not what you are after if you are going to make that kind of a vertical bar. So color bars was one of the things. It was really trendy back in the 80s, and but it needs a stable raster interrupt or a stable raster to actually kind of execute properly. So we know the number of cycles per line. The issue here is that it's different between PAL and NTSC, and there are actually two variants of NTSC as well. So it's either 63 for PAL or something else for NTSC. And for the purpose of this, let's stick with PAL. If you are in NTSC land, you will have to look into what's valid for you instead. But for PAL, it's 63. And there is also this bad line. So on every 8th row, the very first pixel row of a new character row, the VIC steps in, halts the CPU. So the VIC is fetching its stuff, basically fetching the characters for what is supposed to be printed for the next eight lines. And the CPU just sits there, cannot do anything, and it's not really aware that it's sort of being interrupted either. And then the VIC lets go of the bus, and then the CPU can start working again. And if you add sprites, you would have further instances of VIC sort of taking precedence over the bus, halting the CPU. But I mean, most of these things are predictable, or all of them are predictable. If you have moving sprites, it becomes really not predictable at all, but there are tricks to handle that as well. But most of the time you could predict the number of cycles your code is going to have available on every row, which means that if you are going to make code that happens on specific parts of the screen, you can predict at what instruction you are going to, or at yeah, which instruction needs to make that change to the screen if you count the cycles of all the instructions. Okay, yeah, and basically knowing exactly per cycle where you are on the screen, it's the stable raster concept. Okay, let's see if we can move into the next one here. So again, I'd like to make this really clear. I'm not a demo coder. I know basically a number of those concepts, and I played with a few of them, but I'm very far from an expert, but I hope I can still sort of convey the message. And I would like to hear from anybody who disagree with what I have explained here. If I sort of misunderstood any of the concept and I'm sharing sort of the wrong view of this, that would be unfortunate. I hope I have gotten all of it right. Well, at least right enough. And I'm sure a number of you will say that you know this better than I, and would like to kind of tell me that, even if what I've said here would be right. But please refrain from sort of being sort of over cocky and just kind of prove me wrong even if I'm not wrong. But I'm happily proven wrong if I'm actually wrong, right? So the first and sort of simple thing, I've gone through this a bit in the ESCOS article, is the double interrupt. So double IRQ. You are, so again, we will just mention what an IRQ is. Interrupt request. So the CPU is running its course, and then you can set up a number of sources for interrupt requests. And when such an interrupt request appears, the CPU is halting its activities. It's pushing all the current values to the stack, and then it's executing, taking a branch to an interrupt handler routine, which is then run. And when that one is done, it returns, and the normal operation of the CPU is refetching the values from the stack and resuming where it was. So basically the CPU can run, and then it's halted, and it's still the CPU that handles the interrupt. So it's still the CPU, it's just that the CPU is running other things. Think of it like you working, and then you say, and you have your colleague saying, would you like to join me for coffee? And then you go off for 5 minutes having a coffee, returning where you left, and you continue working. It's that the interrupt here is sort of the coffee break. What you do here in the double IRQ is that you have an, and I should also mention here that when the IRQ hits, the CPU needs to complete the instructions. And given that the CPU can execute instructions that are between 2 and 7 cycles long, when you actually start executing that IRQ, the jitter could be between 2 and 7, or you could say up to 7 cycles long. And again, so you need something that handles the potential jitter here of the potential 7 cycles that you could sort of experience. And the first interrupt is triggered on one line, and then that one is going into, it's setting up a second interrupt on like the line before, or sorry, the line after, and then it starts executing a number of NOPs. A NOP is the instruction for no operation. It takes 1 byte and 2 cycles. So when the next interrupt is triggered, you are on, the CPU is executing either the first or the second cycle of that NOP instruction. So you are now reducing the potential jitter of the second interrupt to 2 cycles. I hope that's clear. What you then do is let that second interrupt run. So you have a number of delays until you are at the very end of the screen. If the first interrupt was interrupted by the second interrupt when it was executed the first cycle of the NOP, you read the raster beam, and you are still on that kind of the first row of the second interrupt, that means that you were on the first instruction of the NOP, or the first cycle of the NOP. And if you were on the second cycle, the DO12, so the raster counter, would have wrapped into the next line. So basically the third line here. If you have first interrupt, second interrupt, and then you have like the third line. If you were on the second cycle of the NOP, or the raster was on the second interrupt, the CPU was on the second cycle of the NOP, then the DO12, the raster line, would be on the third row rather than on the second row. And then you compensate for that 1 cycle jitter so that you are perfectly stable. The first interrupt is basically to ensure that you can have a jitter of only 2 cycles. The second interrupt is there to handle that 2 cycle jitter into a perfectly stable raster. This one is sort of simple and straightforward. I mean, if you know your C64 coding and setting up interrupts, this is relatively straightforward. So the difficult part is to ensure that when you read DO12, the raster counter, you need to know which cycle you are on. That like the end, if you are on the first or the second or the third row. It's finding that so you read the correct values there. That is basically the only difficult part about this. And you can do this on every frame, and basically on any line of the frame as well. The negative part of this is that you waste basically 3 raster lines, and given that there are only like 312 raster lines, or 300, it's just over 300 on a PAL machine, or 200 and less, more like 260 on NTSC machines. But so 3 lines is like, let's say that's at least 1% of the available raster time. So I mean, if you really desperately need every cycle, the double IRQ is going to waste at least 1% of the available resources, and they are scarce to start with. So that is sort of the only relevant drawback. It doesn't have very big memory footprint here. It takes rather few lines of code to implement this, and so the only kind of negative issue here is the wasted raster lines. And I've tried to here, I don't know if you can see my mouse pointer, but that is here on the end. So first IRQ is on the first line, and then you have this ring here that indicates if you are reading it on the end of the second, or possibly on the start of the third. Sorry. Oops. Yeah. Okay. That was that. That was one of the methods. We are now going to go through a few of the other methods available, and there are pros and cons, and it might be that you eventually get to the conclusion that you would sort of revert to a double interrupt anyways, but let's at least touch upon the other options. So Pasi Albert Ojala posted this on computer hacking, or Commodore hacking. C equals hacking. I guess it's Commodore hacking then. That was a magazine, text only, that was distributed online. Those are still available if you want to read them, including this one. But he explains a technique to make or to implement stable rasters using using direct memory access and sprites. There is a discussion on CSDB about this, and Gröpas, the guy that's sort of heading Vice, the C64 emulator, and he explains it like the basic idea is to execute a RMW, and so it's read and write instruction in the raster lines where the said sprites are displayed. The missing cycles will force those instructions to get executed in the gaps left by the sprites, which in turn will magically stabilize the whole thing. So again, as described before, on bad lines, you would have the VIC or in this case, I don't think this needs to happen on a, it needs to happen on a bad line, I think. So you need to place a sprite on the screen and ensure that the VIC kind of gets access to the bus and the CPU sits and waits. It is allowed to conclude the instruction it is running, but it has 3 cycles. So this can sort of consume up to 3 cycle jitter. So basically you need to ensure that your main routine doesn't jitter more than 3 bytes. But if your main routine is just a jump to itself, that is a theoretical maximum of 3 cycles. So if your main routine is a jump to itself, then this one could work. And I'm not going to try to explain this in more details. I would encourage you to read the article, and there will be links below to kind of all the techniques here. Most of them are on Codebase 64. There could be a few other sources. I'm not really sure about that when I'm recording this, but there will be links down below. Okay, basically sort of the same trick using another version of it. It's the same kind of core that the VIC is pausing the CPU when it's doing its thing, and then the CPU just sits there or concludes what it's doing. And this is VSP, so virtual screen positioning. On the line, you are forcing the screen to go into one of those bad lines, which means that the VIC will take precedence over the bus and the CPU will sit back. And what happens then is that the CPU is sort of releasing or getting access again to executing its stuff after the VIC has left it. And that means that it's miraculously sort of synchronizing itself. Again, there is a stable IRQ with DMA in Codebase 64, a link down below where you can read about how this works. Yeah, pros and cons. It's very short. It's really short, but it needs to happen on a bad line, and that means that it cannot start basically at the very start of the screen. It needs to happen on a bad line, and that only happens on the kind of the addressable, the piece where you can address with characters. It cannot happen in the border. And then VSP in general is sort of not encouraged because there are a number of machines that cannot handle VSP, and if you start messing with VSP, the CPU will crash because it starts writing crap in memory. Some machines are always like that, or they are like that when they are warm or when they're cold. So it's not advisable to use VSP. The probability of this happening if you're just synchronizing your raster once using a VSP is of course very small, but it can still happen. So yeah, be aware that you should all use this with caution. A rather new thing, Pier Giorgio mentioned this, and he has been playing with this to find out, and this is basically how I started kind of investigating here and preparing for this presentation. So he made a really efficient implementation of this theory, but the general concept is also kind of touched upon in Christian Bauer's Vic article. And Christian Bauer is the guy that did Frodo, basically the first relevant C64 emulator on the C64, or yeah, on multiple other platforms. Frodo is available on mobile. It's available on Amiga, yeah, PC, Mac, and a number of other platforms. It wasn't cycle exact, but Christian sure knew how cycle exact implementation would look like. But basically, Frodo is really old, so back at the time there was no CPU power to back cycle exact implementation. So this was before CCS64 was emerging, and then was basically the first implementation of a cycle exact emulator. There is also a code-based implementation, which is really complex, and it includes interrupts and stuff, whereas Pier Giorgio's implementation is without interrupts. It's sort of a delay loop, and then it starts. Just to briefly touch upon how this works, and again, I'm not really sure if I understand this, but on the C64, you could connect a Lightpen to one of the ports, the joystick ports, and then you place the Lightpen on the screen, and if you have set up an interrupt, a Lightpen interrupt, that Lightpen will latch sort of an interrupt when the raster is sort of painting the pixel under where the Lightpen is pointing. This technique sort of uses that, but you don't need a Lightpen. But what it does is fiddling with one of the data directions on the CIA, the timer chip, which is connected to the joystick ports. And when doing that, it then reads DO13, which is the latch X position of the Lightpen. And then you do a bit of clever code after that to kind of determine where you are on the screen and adjust accordingly. And then you have a stable raster just after that. It's a bit of a black magic, but there will be a link both to the Codebase 64 original implementation of this, and there will also be a link to Pier Giorgio's implementation of this. It's a GitLab project or a GitHub, I don't remember which. It's sort of one of the Git repositories, and you can just download it from there, and it's fine. I mean, pros and cons. It's really elegant. To be honest, it's really, really elegant. And it doesn't use any IRQ, so you don't need to set up anything like that. You can set up it to work on basically any raster line. It's not one of those where you need to be on the visible sort of the screen inside the borders. But then you need to tweak the original code, of course, to make that work. And if you don't understand it, it's very difficult to tweak it to make it work. And one of the other thing is that you can only use this once per frame. So if you would like to make an adjustment to make a stable raster on the very top of the screen, run a bit of a music, which could take any number of cycles. It's not predictable how many cycles it would take. And then on the lower part of the screen, you would like to make another stabilized raster to ensure that you know where you are. Then you cannot use this technique. It can only be used once per screen. And given that this handles CIA1 and DCO3 here, so it's CIA1. In theory, at least, it could be trashed by key presses. I'm not saying I've managed to kind of make it not work, but at least there is a theoretical risk of key presses messing this up. Yeah, that's that. Okay, these are kind of ways to deduct where you are on the screen. So you have a stable raster. But you need to kind of revisit them. You need to stabilize again as soon as you release control over the number of cycles you have executed. you need to recalibrate in order to kind of regain perfect control. And that could be rather difficult if you need to make it several times on the screen. And as you saw, a few of those techniques actually was only available to you at once per screen. So, but one of the things you can do is set a timer on the CIA, which automatically loads itself with default value and starts counting again. So there is a counter which you can set to 63 cycles. You start it, and then after the 63 has counted down to 0, it starts with 63 again. So the beauty of this is that the timer would exactly match the sort of the inverse of, or basically it will count how many cycles do I have remaining on the current line I am on. If you ensure that countdown happens totally synchronized with the screen, reading the value from this CIA would give you where you are on the screen, but in reverse, or how many cycles you have left on the screen. Applying that technique together with a clock slide, you can have a perfectly stable interrupt, basically at will. The clock slide, which I'm going to link down below, is the one by LFT, and LFT is also the guy that has done Spindle. And my understanding is that Spindle gives you this automatically. So if you are implementing a demo using Spindle, which is sort of generating the track loader mechanism for a valid demo, he implements this for you. So you can read the CIA timer and you can get that value directly. Unless you do funky stuff with the timer yourself, then that is available to you. And the cool thing here is that this runs totally independent of anything else. So if the CPU is halted, or the VIC take precedence, or this is an interrupt or a non-interrupt, or you put graphics on the screen and what have you not, nothing of this would change the CIA timer because it runs totally independently. So whenever the CPU has access, you can read from the CIA and you would get a valid reading from the CIA where you are on the given raster line that you are currently on. And of course you can read from DO12 telling you which raster line you're on. So basically this tells you that you need to synchronize at least once, update the CIA with a value such as this, and then you can use the CIA plus a clock slide to ensure that you are stabilizing your routines. Okay, so I hope you understood the main concept here. Obtaining a stable raster is super important for doing your demo stuff on the C64, because most of the tricks that you would eventually need to implement, they are relying on perfect timing of splits, or opening the borders, the side borders, upper and lower. They are less precise. That's not a per cycle exact thing, but side borders is for sure like that. So this is why understanding how to obtain stable rasters is important if you're going to be a successful demo coder on the C64. That was everything we had for today. It's a really technically complex area, and I'm just hoping I made it justice. I'm not sure I did that, but at least if you're a competent demo coder already, I'm sure you knew all of this. And if you are a demo coder in the making, at least I hope I've given you pointers on where to find additional information of this. There will be links down below, and I hope these will be pointing to the relevant sources for your further studies. I should also say that I'm recording this in the end of June, which means that summer is coming up, and I will have holidays, and I will be out of my normal kind of work environment where this is recorded, which means that there might be a few weeks before you see any new episodes coming up. Take the time to do what TV is doing, watching reruns. We have 79 previous episodes, so take the time and look back on the catalog of the number of releases we have before. Possibly a few of those could be really interesting for you to watch them again if you've seen them already, or see them for the first time if you've missed them the first time around. So have a very, very brilliant summer, and yeah, let's meet when we meet again. Bye bye.